Yes, so this is the last chapter that we'll be covering this semester.
Professor,
Yes.
I don't see chapter 9 notes in the modules.
They're labeled chapter 10.
Oh, okay.
Yep. It's just because we're skipping over one chapter to get to this important chapter.
Okay.
Yeah.
Thank you.
Mm-hmm. Okay, so let's get started talking about organohalides. So they're an organic compound containing at least one carbon-halogen bond. Now, the degree of unsaturation is 0 for each alkyl halide. The halide just simply replaces a hydrogen. Now, just like any functionality, let's talk about how we name alkyl halides. So first and foremost, you're going to find the longest chain, and then you're going to name it as the parent chain. Okay? You want to make sure that your longest parent chain contains the double or triple bond if it is present. You're going to number from the end nearest to any substituent, be it an alkyl group or a halogen. You're going to identify and name the substituents, and then you're going to name the parent chain and assign each substituent. So in terms of priority, alkenes and alkynes take priority over halides and alkanes in terms of numbering. With all else being equal, you're going to number carbons so each atom has the smallest possible locant number. Halogens as functional groups are indicated with halo prefixes. So bromo for bromine, chloro for chlorine, iodo for iodine, fluoro for fluorine. Now, halogens don't take priority over alkenes. They're just another functional group on the list. So you want to assign the lowest possible locant numbers, and if there's to each of your substituents. If there's a tie, then and only then do you resort to alphabetical order. Such as in these two examples, for example, if we compare our alkyl and our halogen substituents, we want the lowest possible numbers for each of our substituents. So we choose to number from left to right over right to left. And let's show why that is. So looking at our potential numbering pattern, we see very clearly that if we chose to number from right to left, we'd have our bromine at position 3, our methyl at position 4, and a methyl at position 6. If we compare this to our numbering method in red, where we have our methyl at carbon 2, a methyl at carbon 4, and a bromine at carbon 5, we see that we have overall that our numbers are lower and our starting number is lower for each of our substituents using the numbering method in red. So the halogens don't get any special priority over alkyl groups. Does that make sense so far in terms of naming alkyl halides? Treat your halogens like just another functionality, like just another alkyl chain, for example. So let's do a few examples now. So I'll do the first one and you'll do the second one. So first we're going to entertain all of our different numbering possibilities for the longest chain. So let's consider if we numbered from left to right, and let's consider if we numbered from right to left. So if we compare our numbering conventions, if we number using the numbering method in blue, we have a methyl at positions 2 and 3 and a chloro at position 4. Using the numbering method in red, we have a chloro at position 3 a methyl at position 4, and a methyl at position 5. So which method is preferred? Which numbering method gives us the smallest locant numbers for each of our substituents? The method in blue or red? Which method gives us the smallest locant numbers? The method in blue or red? Blue. Okay, so we name this as 4-chloro 2,3-dimethyl. And since this is a 6-carbon chain, we call this hexane. Would someone like to tell me, why did I place chloro in front of dimethyl? What rule am I following here? Why do I place chloro before dimethyl in the name?
That rule?
What was that?
Alphabet?
Yep, alphabetical order, exactly right. So remember, you order your substituents in the name in alphabetical order. So let's take a look next at the following example, and I'd like you to name the following molecule. And don't be shy to break out the annotate feature or to type the name in the chat. And we'll come together as a group to discuss in about 3 to 4 minutes. And don't be shy to break out the annotate feature or type your proposed name for this compound in the chat. Otherwise, we'll discuss in about 2 minutes. And don't be shy to type the name in the chat. We'll discuss in about 1 minute. Okay, so we have some names proposed. So looking at the numbering convention, the numbering method provided looks good so far. So let's try to name this compound using that numbering convention. So allow me to clear these annotations. And let's start naming this compound. So first and foremost, we want to have the smallest carbon locant numbers for each of our substituents. So we'll name from right to left. So naming each of our substituents. So this group is an isopropyl. This group is a methyl. And we have an iodo functionality. So we'd name this as, so in terms of ordering, do we count the iso prefix in the name? Do we count the iso prefix? Yep, so the iso prefix is considered in terms of alphabetical ordering. So if we compare iodo and isopropyl, the iodine is first alphabetically, so we name this as 2-iodo, 4-isopropyl, 3-methyl, and since we have 6 carbons, this would be hexane. Perfect. Okay, let's do another example. So in terms of our priority list so far, so alkenes and alkynes take precedence over your halides and alkenes. So when you're dealing with an alkene or an alkyne, you're going to number your carbons so the highest priority group has the lowest locant number. So let's look at this alkyne, for example, 1, 2, 3, 4, 5. So that's one method. Or we can number from left to right, 1, 2, 3, 4, 5. In this case, the method numbering in red takes priority because we want to assign our alkyne the smallest possible number. So we name this as 4-chloro, 3-methyl, 1-pentyne, where this "-ine" ending is signifying we have an alkyne. I'd like everyone now to take a moment and to look at this first example and to try to name this compound. Remembering to number your carbons to give the smallest locant number to your alkene or alkyne starting carbon. So let's take about 2 to 3 minutes to work on that. And don't be shy to type your response in the chat or write your response using the annotate feature. And don't be shy to type your proposed name in the chat for this compound, and we'll discuss about a minute and a half. Okay, so we have some proposed names in the chat. So if we want to number our carbons to give us the smallest possible locant number for our alkene, we'd number from left to right So we name this as 4-chloro-1-butene. Yep, perfect. Okay. So just as a side note, in the event of a tie, you're going to assign the smallest carbon locant numbers to substituents in alphabetical order. So if we have a fluoro substituent versus an ethyl substituent, what should get the lowest locant number? Fluoro or ethyl? Which functional group is first alphabetically? Ethyl, right? So we name this as 1-ethyl, 3-fluoro, cyclohexane. Perfect. Let's look at this next example. I'd like you to take about 1 to 2 minutes and to try to name this following second compound. So we have some reasonable responses proposed so far. So let's talk about this example now. So we have a chloro functionality. We have a methyl functionality. So what is first alphabetically? Chloro or methyl? Chloro. So we'd name and we'd number this compound from left to right. So we'd call this 2-chloro, 4-methyl, pentane. Perfect. The responses in the chat were spot on. So now that we've had a chance for some revision and adjustment after seeing these next few examples, I'd like you to take a look at the following example and try to name this compound. We'll discuss this in about 2 minutes, and don't be shy to type a proposed name in the chat for this compound. Yep, exactly right. I see a lot of reasonable responses in the chat. So if we compare bromo and chloro, bromo is first alphabetically. So we'd number from right to left. So we'd call this 2-bromo, 4-chloro-pentane. Perfect, perfect. Okay. So let's talk next about the structure of alkyl halides. And let's talk about some bond energies. So the carbon-halogen bond is longer as you go down the periodic table, and the carbon-halogen bond is weaker as you go down the periodic table. So if we look at our typical carbon-halogen bond, the carbon-halogen bond is polarized, where the halogen has a partial negative charge and the carbon has a partial positive charge. This carbon is electrophilic. When you think about alkyl halide reactivity, I want you to draw this really harsh dividing line. So fluorine, then chlorine, bromine, and iodine. So fluorine and carbon-fluorine bonds are typically not reactive. So when you see a carbon-fluorine bond, I just want you to remember that they typically don't react in the same way that alkyl halides such as chlorine, bromine, and iodine react. And that's simply because the carbon-fluorine bond is super strong. And fluorine itself, being so small and electronegative, it is not as effective of a leaving group in many reactions that we'll see coming up, okay? So when you think about alkyl halides in terms of synthetic usefulness for many of the reactions that we're going to discuss in this chapter, the alkyl fluorides behave fundamentally differently in many of these reactions than the chloride, bromide, and iodide. So for most synthetic reactions in terms of displacements and eliminations, they only work efficiently under standard conditions with the chlorides, bromides, and iodides. Does that make sense to everyone? There's one thing I want you to take away. Fluorine behaves differently than your other alkyl halides. Does that make sense to everyone? Can I get some responses in the chat? This is a preface for a common trick question that we'll see later on in this chapter. Okay, so in terms of how we make alkyl halides from alkenes, a nice go-to method is allylic bromination. So if you add N-bromol succinimide and light, the light indicates that we are functioning through a radical mechanism in most cases. So in this case, we can selectively react our allylic positions. And the reason why our allylic positions are selectively brominated is because an allylic radical is quite stable. So allylic radicals are stable, at least relatively speaking. So then, for allylic bromination, after we generate our bromine radical, the bromine radical can abstract a hydrogen, and we of course generate a very stable allylic radical. This allylic radical can then react with another equivalent of bromine in order to generate an allylic bromide. So let's take a look at the following reaction and let's draw a complete mechanism. And from this mechanism, we'll be able to explain why product A is favored over product B. So first and foremost, N-bromol succinimide will generate a trace amount of bromine. So under radical conditions in the presence of light, we can cleave our bromine-bromine bond and generate two bromine radicals. Okay, now after initiation, our bromine radical has a choice. It can either abstract hydrogen A or B. Which radical is more stable? Which radical is more stable? B would lead to a secondary allylic, while A would lead to a tertiary allylic. Which radical is more stable, A or B? I see a lot of people typing A, and that's exactly right. So we're going to abstract our radical, and in turn, we're going to generate a tertiary allylic radical. Now that we have a second bromide radical, we can combine with our second bromide radical and we'll selectively generate our tertiary bromide. So you can get regioselectivity from allylic bromination. Does that make sense to everyone? Does everyone understand mechanistically what's going on? This is a typical radical chain reaction. So that's why we're using these fishhook or one electron movement notation. Any questions on this example? Any questions on this example? Okay, so let's talk a little bit about uses for allylic bromination. So in a two-step sequence, we can brominate the allylic position and then eliminate it to generate a diene functionality. You'll need this a little bit later in Chem 113 when you want to do like a Diels-Alder reaction or a paracyclic reaction. So mechanistically, just like before, we have our two allylic positions. This time the allylic positions are identical. Our bromine radical abstracts a hydrogen. And then our allylic radical combines with our bromine radical to generate an alkyl bromide. From here, potassium hydroxide then removes a proton and we eliminate our allylic bromine. And that in turn generates a diene. This second reaction is known as an E2 reaction or an elimination reaction. We'll be seeing a lot more elimination reactions later on in this chapter. Any questions so far on the preparation and uses of alkyl halides? Okay, so let's keep going and let's develop a few more things. So alkyl halides will react with nucleophiles and bases. So alkyl halides are polarized at the carbon halide bond, making the carbon electrophilic, carbon delta plus. Nucleophiles will replace the halide in carbon halogen bonds of many alkyl halides. Nucleophiles that are Bronsted bases produce elimination. So our two main pathways for alkyl halides are substitution, where we replace our alkyl halide with a nucleophile, or elimination, where our base removes a proton and we eliminate our halide. So substitution versus elimination. We'll discuss how reaction conditions can be tuned to favor substitution or elimination, and we'll discuss the stereochemical and the stereochemical outcome of these reactions and any regioselectivity we can observe. But the key thing, alkyl halides can react via substitution or elimination mechanisms, depending whether you have a nucleophile or a base. Now, an interesting case study that prompted multiple investigations into nucleophilic substitution reactions was the Walden inversion. They showed that you can take malic acid and convert it to the opposite enantiomer via a series of chemical steps with achiral reagents. So clearly throughout this sequence, the stereochemistry at our malic acid stereocenter underwent an inversion. This really prompted a lot of study into substitution reactions as a means to take material with defined stereochemistry and convert it to products with a different yet still defined stereochemistry. This is very powerful. So let's talk about these fundamental reactions. The first of which we'll discuss is the SN2 reaction. So S for substitution, N for nucleophilic. Oops, one moment. And 2. And this 2 says both our nucleophile and substrate react in the characteristic step. So this is a bimolecular process. So let's talk about kinetics really quickly, as a lot of these reactions were classified by studying their kinetics and determining their rate law. So the rate is the change in concentration with time. So rate can be thought of as the change in concentration over time. The rate depends on the concentrations, temperature, and the inherent nature of the reaction. A rate law describes the relationship between the concentration of reactants and the rate of conversion to products. The rate constant is a proportionality factor between concentration and rate. Now, the rate law is a result of the chemical mechanism, and the rate law describes the rate limiting step. Of a reaction in most cases. So we see that the rate law for an SN2 reaction is dependent on the concentration of our halide and our nucleophile. So then, this reaction follows second order kinetics and depends on the concentration of our substrate and our nucleophile. The fact you see both concentrations in the rate law suggests this is a bimolecular process. We need two species reacting in our rate determining step. And this is revealed and quite clearly shown in the mechanism for the SN2 reaction, where in the SN2 reaction, we have our nucleophile attacking our electrophilic carbon and our leaving group leaves. So nucleophile attacks, and our leaving group is displaced. Now, as a transition state in this reaction, we have the following transition state where our carbon nucleophile bond is forming and our carbon leaving group bond is breaking. Now, by looking at this transition state and analyzing the potential steric environment of this transition state, we can begin to understand how the SN2 reaction is sensitive towards variations in the substrate, the nucleophile, and the leaving group. At the end of this process, after our nucleophile displaces our electrophile, we clearly see that we have an inversion of stereochemistry. So our stereocenter has completely flipped in terms of its configuration. Now, the reason why the nucleophile attacks opposite to your leaving group is that the nucleophile is engaging and attacking the sigma star of your carbon leaving group bond. So let's draw out a brief MO orbital picture. Let's draw out a brief molecular orbital picture to begin to rationalize what is being observed so far. Okay, so let's draw out. So we have our sigma bonding MO. So this is our carbon leaving group, sigma bond. Our opposite to this sigma bond is a sigma star. And where is the sigma star? Where is the anti-bonding orbital located for a sigma bond? Where is the anti-bonding orbital located for a sigma bond? Is it on the same side or is it on the opposite side of your sigma bond? Where do I draw the sigma star? Where is the sigma star? It's on the opposite side. So drawing out, we have our sigma star, or our carbon leaving group bond. Our nucleophile is attacking the sigma star, and as a result, it weakens your sigma bond. So that is why an SN2 reaction is often called a backside attack reaction, because the nucleophile attacks, so the nucleophile attacks the opposite face to the leaving group. Does that make sense to everyone? So the nucleophile's approach is constrained by the location of the sigma star orbital. The nucleophile will always attack opposite to your leaving group in an SN2 reaction. This is a concerted process, so this occurs in a single concerted step. That's why our rate depends on the concentration of our nucleophile and our substrate. Okay, so let's practice drawing some mechanisms and let's look at the transition state. So after the nucleophile attacks 180 degrees from our leaving group, we end up with this planar transition state where we're forming a bond with our nucleophile and breaking our bond with our leaving group. And at the end of this process, we have a geometrical inversion. We've completely inverted our stereocenter. Okay, so let's draw a mechanism for the following SN2 reaction. So in this case, our nucleophile is sodium ethane thiolate. So if we're drawing this in arrow pushing mechanisms, our sulfur will attack our electrophilic carbon and we will displace our leaving group. Common leaving groups are overwhelmingly alkyl halides in this chapter. Now, as we notice, if we compare our two stereocenters, we observe an inversion of configuration. What do I mean by that? Well, if we look at this first stereocenter, this center has an R configuration. This center has an S configuration. So as we can clearly see, the stereochemistry at this stereocenter has been inverted. To show everyone what this looks like from a 3D model perspective, One moment, let me just get this perfectly adjusted. Okay, so here's our alkyl halide. Initially, our halide's pointing towards us. The sulfur is going to attack from behind. It's going to attack from the opposite face. And we're going to invert our stereocenter. So when we attack from the opposite face, from behind, and we invert our stereocenter, now we have our sulfur atom pointing away from us. If we look at our dash wedge notation, we clearly see that the sulfur is now pointing away from us, and this stereocenter has the opposite configuration. It's now an S stereocenter. Does everyone understand this key idea that the SN2 reaction occurs with inversion of configuration? Okay, perfect. So make sure to note that. The nucleophile is attacking from the opposite face. Okay, so with that in mind, I'd like you to take a look at the following SN2 reaction. I'd like you to draw a mechanism for this reaction and predict the products. Just as a side note, DMSO looks like this. DMSO is not a nucleophile. Sodium chloride, we have chloride floating around. And with that information in mind, I'd like you to take about 2 to 3 minutes to try to draw the products from this SN2 reaction. And I'd like you to be very clear about the stereochemistry of your products. And don't be shy to break out the annotate feature and draw your proposed products for this reaction. If not, we'll discuss in about another minute and a half. Yep, perfect. So let's just draw out an instructor solution, but that mechanism looks perfect and the products exactly are drawn with inversion of configuration. So our nucleophile attacks our electrophilic carbon and bromine is displaced, and we end up a product with inversion of configuration. Unfortunately, in this case, this substrate is meso, but we do get the point that if this substrate was chiral, then our product would also be chiral with inversion at the stereocenter. Perfect. So let's keep going now, and let's think a little bit about steric effects on the SN2 reaction. So here we're looking at pictures as we add alkyl groups. So if we're looking at a methyl comparing a methyl to a primary, secondary, and tertiary halide as we try to approach when we go from a primary, secondary to a tertiary. My question to all of you is the opposite side to our bromine more or less accessible as we add substitution? Is it easier or harder to attack the sigma star as we have more alkyl groups on our carbon? Is it easier or harder for an SN2 reaction to occur when we have a greater amount of substitution? It's harder. There are just more things blocking your approach, and your transition state becomes higher and higher in energy the more steric interactions you build up. So increasing substitution results in a slower rate of reaction. Perfect. In terms of rate of reaction, the methyl primary and secondary are your main substrates for the SN2 reaction. The neopentyl and tertiary alkyl halides do not typically react efficiently under SN2 conditions. Now, one thing I want you to bring your attention to is that in the neopentyl halide is that adjacent steric adjacent groups can block the nucleophile. So in this neopentyl group, you have this giant bulky substituent that in turn impedes the SN2 reaction and the attack onto our electrophilic carbon. So the SN2 reaction is very sensitive to the steric environment, to all the substituents surrounding your alkyl halide. So the one thing I want you to note is that tertiary species do not react under SN2 conditions. Likewise, your vinyl and aryl groups do not typically react under SN2 conditions. So we're going to pick up on this topic next time, as it's tied very closely to elimination reactions, and I want to make sure we cover these topics together as a package group. So we're going to continue on, and we'll finish up this chapter in lecture and lab next class session. So with that, let me just pause the recording and